Hi everybody, this is Mr. Parliament, and this is a video tutorial walking you guys through question 5 of worksheet 6.5. So, first of all, question 5 asks that basically the setup is there's this point P right here that I've represented with an X. There's a ball that's dropped from a tall building, and what they ask you to do is graph the magnitude of the angular momentum versus the time that has passed. First of all, what I've done here on the left is I've drawn the picture twice, each picture representing different information about the problem. To start with, we have the ball at its initial height, and I drew a triangle. The hypotenuse of that triangle is the distance from point P to the ball, which I called R naught. H naught is the height that the ball is above point P. Note that that's the height from point P, not the height from the ground. And then X is the base of that triangle, the distance from point P to the ball in the X direction. So the purple triangle represents the initial position of the ball. The dotted lined ball right here represents the ball some arbitrary amount of time later, so t seconds later. And again, I've drawn a triangle with the hypotenuse, which I called R, going from point P to the center of the ball. The height of that triangle, H, is the height above point P, and the base is, again, from point P to a position right under the ball. Notice that X doesn't change because the ball is falling straight down. All right, on the next picture, I drew some dotted lines that basically represent if the ball was moving in a circle around point P, that's what that circular path would look like. So Cody emailed me with an interesting question a couple of nights ago, and he was asking, okay, why do we want to calculate the angular momentum of something that is moving linearly? And the answer is that it's kind of a what-if calculation. What if something were to happen that would cause the ball to start moving about point P in a circle? And if that happened, angular momentum would be conserved. So maybe there's some sort of catcher right under the ball that the ball is going to fall into, and then that starts moving some arm about point P. Maybe point P is actually Spider-Man, and Spider-Man is planning on shooting a web at the ball and catching it, and then causing it to fall in some circular path. Whatever the scenario is, angular momentum would be conserved. So even though the ball isn't moving angularly yet, it is still useful to calculate its angular momentum. All right. So those are those pictures. Now, let's move on to actually calculating the angular momentum. So we know that the angular momentum vector is equal to the cross product of the linear momentum vector and the radius of your circle. Now, we don't get too heavily into cross products and dot products in this class. The result of two vectors crossed together is always a vector. But if you're just looking for the magnitude of a cross product, you can use a shorthand that the magnitude of the cross product of two vectors is equal to the magnitude of the two vectors multiplied together times the sine of the angle between them. The mnemonic device I like to use for that is cross sign. So cross product, the magnitude is the two magnitudes multiplied together times the sine of the angle. Dot product, on the other hand, you use the cosine of the angle. So that works for any two vectors cross-product together in 2 dimensions. All right, so if we look back to our bottom picture, we can see that as the ball falls, this dashed line right here that represents a path tangential to our circle is getting closer and closer to our velocity vector for the ball. So that angle theta is getting smaller and smaller. And it happens that this angle theta is the same as this angle theta, the angle of our triangle. Those two triangles are similar. We can prove that with angle theorems. I tend to have more of an intuitive approach of just realizing that those two angles are linked in this problem. As this triangle gets flatter and flatter, as this theta gets closer and closer to 0, this angle will get closer and closer to 0 as well. If this angle was actually 0, if this triangle was just a flat line, well, then our tangential velocity vector and a regular velocity vector would be perfectly lined up with each other, so the angle between them would be 0. So we're not actually interested in that angle theta. We're interested in the angle between the radius vector and the velocity vector. But because the radius vector and that tangential velocity vector have to be at a right angle to one another, it's by definition tangent to a circle, that means that the angle between the radius vector and the actual velocity vector is 90 minus theta. So that's why this sine is actually of 90 minus theta, because it's the angle from here to here. So we can start to plug things in and simplify this. Momentum, you guys know, is m times v. We found the magnitude of that momentum vector, so this v is just going to be some positive value. It won't be a vector anymore. And then magnitude of the radius vector is just r. And you guys probably know from trigonometry that sine of 90 minus an angle is the same thing as cosine of that angle. Cosine and sine are just the same function phase shifted 90 degrees. All right, so we've got an equation for the magnitude of angular momentum. The magnitude of angular momentum equals the mass of the ball times the speed of the ball times the distance from point P times the cosine of that angle theta. So if we want to get that in terms of t, we need to get an equation for v in terms of t, an equation for cosine theta in terms of t, and an equation of r in terms of t. Mass is a constant, so that equation would just be mass equals mass. You might be wondering why I'm doing it in the order of v and then cosine of theta and then r. That's because I solved the problem before doing this and realized that we actually don't need r, and we'll get to why in a bit. So, to start off with, an equation for v, the speed of the ball. Well, we know that one of our kinematic equations is that velocity equals acceleration times time plus v naught. V naught in this case is 0 because the ball is dropped from rest. Acceleration would just be the acceleration due to gravity. So that simplifies to v equals g, the acceleration due to gravity, times time. So I'll just leave that as a variable g for now, or I guess a constant g for now. But you guys know that on Earth that's equal to 9.8 meters per second squared, or about 10 meters per second squared. All right, so next we're going to get an equation for cosine of theta in terms of time. So to start off with, I'm going to take this triangle right here, the red triangle. We've got a hypotenuse r, a height h, and a base x. And we can use trig to get an equation for cosine of theta. So cosine of theta is adjacent over hypotenuse. So adjacent would be x, hypotenuse would be r, so cosine of theta equals x over r. So we could get an equation for r in terms of t to get this in terms of an equation for cosine of theta in terms of time, but if you stop and look for a moment, we've got an r in the numerator here, and then as a part of this cosine of theta, we've got an r in the denominator. So I'm actually going to stop there. I'm just going to leave it as an equation of cosine of theta in terms of x and r. So now we can start plugging stuff in. The angular momentum equals the mass of the ball times g times time. So that's just mass times our first equation for velocity times radius r times our equation for cosine of theta is x over r. So the r's cancel out. That leaves us with the angular momentum about that point P is equal to m times g times x times time. So we've got three constants multiplied together. Mass isn't changing, the acceleration of gravity isn't changing, and x isn't changing. times our variable time. So that's going to give us a straight line. And in fact, I've graphed it in Wolfram Alpha. I went ahead and just said it was a 1 kilogram ball and that x was 1 meter. So that leaves us with 10 times time, and that is in fact a straight line. I drew mine as a positive line because v in this case represents the speed of the ball, not the velocity of the ball. All right, so there's question 5. Feel free to email me if you have any questions. Awesome, thanks, bye.